everybody. Let's get a little bit of practice with conservation of angular momentum. So let me just make up a problem here. So let's say you have a pottery wheel that's rotating this fast, some initial angular velocity, and then we know the mass, and then let's just model it as a disk like this. So we know the mass and we know the radius. And we know the angular velocity. Okay, and then you drop a ball of clay onto the pottery wheel. So let's say a ball of clay right here. Okay, and then we know the distance is some distance d between the center of the pottery wheel and the center of your ball of clay. So that's given. And then let's say we know the mass of the ball of clay and we know the radius of the ball of clay. Okay, so we're given these numbers and also the distance d. We're given these numbers. Solve for the angular velocity after you drop the ball of clay on the pottery wheel. So what is this? Okay, so how do you do this? What is conserved? Angular momentum is conserved. Right, so the angular momentum initially is the same afterwards, final. So what is the angular momentum before over here? I omega. The angular momentum after I omega. Okay, so then this is what we're after. So as long as we know, and we already know this, so we just need to figure out these two things and then we're good. Okay, so what is the moment of inertia of the pottery wheel? It's just right here. 1/12, 1/2 m for the disk, r for the disk squared. Okay, done. What is the moment of inertia over here afterwards with the ball of clay sitting on it? Okay, so it is the pottery wheel, 1/2 m r squared, plus the ball of clay. So ball is like right here, solid sphere, 2/5 m r squared. But that's the ball about its own center of mass. It's not rotating about its own center of mass. It's rotating about the center of the pottery wheel. So plus extra. How much extra? The mass of the ball of clay times the distance between the two parallel axes squared. So what's the distance between the two? Right here, distance d. So there we go. This is the moment of inertia after we drop the clay on the pottery wheel. All right, so now we got everything we need to solve for that unknown. Okay, let's try another example. Let's say you have a pendulum that's like you're testing out wind turbine blades. So let's say you have this pendulum at rest. It's a bar and then a slab like this, a slab. Okay, and then we know things like we know the mass. I'll call it mass of the bar. We know the length, then mass of the slab, and then we need to know the dimensions. I'll just call this B and this A just so it looks like the picture. Okay, and then let's say we fire a bullet that represents like debris hitting the turbine blade, and let's say it hits over here. So we fire a bullet that's like debris, some velocity, I'll call it mass of the debris. Okay, and then it hits right over here. And I'll just make up some 3/4 of the way down. Okay, so what is conserved in this collision? Angular momentum is conserved, right? Because after the collision, the pendulum is going to swing with some angular velocity like this. Okay, so angular momentum is conserved. Okay, what is the angular momentum before the collision? So if this turbine blade is at rest, I omega would be 0 because it doesn't have any angular velocity. But then there's angular momentum due to the debris about some point we can choose. So let's say we find the angular momentum about the hinge over here, the hinge, and then here's the debris with some mass going some speed. So what's the angular momentum of this debris about this hinge? It's R cross linear momentum, mv. Right, so let's say it hits horizontally, so then these are perpendicular. So it would be 3/4 L times mass velocity. Okay, so that's the angular momentum of the debris about the hinge. And then after the collision, we're still considering the hinge. So what's the angular momentum about the hinge? Now it's that pendulum, the wind turbine blade, with that debris stuck to it. Let's say it gets stuck. So I omega. But then what is the moment of inertia of this turbine blade with the debris stuck to it? About the hinge, right? This is about the hinge. So about the hinge, right here. For the bar, the center of mass is here. And then we got the debris, and then we got the slab. Okay, so for the bar, this, the moment of inertia is 1/12 m L squared, which I got from right here. This is from the previous problem. Right here, this is the bar. 1/12 ml squared. Okay, but then the bar is rotating here. We need it to be here. So parallel axis theorem plus extra. How much extra? The mass of the bar times the distance between these two parallel axes squared. So how far is that? L over 2. Okay, now the debris. What's the moment of inertia of the debris about its own center? Let's say it's a dot, a point mass, a particle. So in your mind, you can think of it like, imagine it's like whichever one of these, like a solid sphere, where the radius, take the limit as the radius approaches 0. The moment of inertia of a point mass about its own center of mass is 0. But then it's not rotating about its own center. It's not rotating about here, it's rotating about here. So how far is this? What number did I say? 3/4 L. So the mass of the debris times 3/4 L quantity squared. Okay, and then now the slab. Let's see. Okay, so the slab is right here. 1/12 m a squared plus b squared for the slab. 12th a squared plus b squared, but that's here. We need it to be here. So plus extra. How much extra? The mass of the slab times this distance squared. So how far is that? Here to here is L. Here to here is B. So here to here is B over 2. L plus B over 2. So all of this is the moment of inertia of the wind turbine blade with the debris stuck to it about the hinge. So all of that is this. Okay, and then, I mean, we could continue with this problem, like what happens if the entire thing swings up over here? And then I ask, for example, like how high, what is the angle? To what angle does it swing? And then you could do that, right? Because you know the moment of inertia. We know this omega. So then how would you do it? Energy, let's say, is conserved. So initially, about, let's say, the hinge, 1/2 mv squared for the hinge, which is 0, right? This plus 1/2 I omega squared for the hinge, which we just solved this right here. And then that's kinetic energy. What is the potential energy? Depends on where you pick the datum. So let's say you pick the datum here for everything. You can, of course, choose one datum per mass, but then I'll just pick it like this. So there's the bar, the debris, the slab, right? The bar, the debris, the slab. So what's the potential energy for the bar below the datum? mg L over 2. For the debris g 3/4 L, and then the slab minus slab g L plus b over 2. Okay, so this is initial, and then final. At the highest point, it's at rest. So the kinetic energy is 0, so it's just potential energy. So then after it swings, final, it's just gravitational potential energy, right? So for the bar right here, bar g L over 2, and then how far is this? That's opposite the angle, cosine theta. The debris, this should be a minus. Debris, 3/4 L cosine theta, and then for the slab, L plus b over 2 cosine theta. And there we go. There would be only one unknown left, which is the angle. Okay, so I hope that was helpful as a review. That was a lot of material, so let me know if you have questions, and I'll see you on the next video.